We're going to talk more about that later, but let's get back to our friend the ice table.
Okay. In the equilibrium below, okay, so I have 2HI becoming H2 and I2 at equilibrium. Okay? I've given you the equilibrium constant. Kc equals 1.26 times 10 to the minus 3. There are lots of reactions with known equilibrium constants. Somebody probably calculated it the way we did in class last time. Okay? Some of them you can look up in books. I have given you concentration HI. What does HI sub 0 mean? Initial concentration. Okay. That could also be written HI-INIT. That's how it was in your lab. Okay. But that sub 0 could mean at time 0. Okay. So I've given you that. I need to know all the equilibrium concentrations from that one initial concentration and the equilibrium constant. Okay? So we can start by filling out the ice table with what we know. Where's that 0.24225 going to go? Underneath the 2i in HI in the initial row. 24225. Okay. If I give you an initial concentration of one thing and no products, what did I tell you can assume about the products? 0. Okay. What are we going to put in this change column? What's change going to be for the H2 and the I2? What do you think? Is it going to be positive or negative, first of all? It has to be positive because we're starting out with none of H2 and none of I2. So going to equilibrium, we have to be increasing that by some amount. Okay. The variable we used, remember, was x. Okay. What about HI? How is its concentration going to change as it goes to equilibrium? It will decrease. How can we put it in variable terms like that? It is minus 2x. Why is it minus 2x? Because of the coefficient. Because every one H2 we make requires 2 HIs. Okay? So, fair enough. The concentration at equilibrium of HI in these terms would be 0.24225 minus 2x. Right? And the concentrations of these two products at equilibrium in these terms would just be x for both of them. Okay? Yeah.
Could you break it apart into 3 terms again? Would they all be x?
It depends on the coefficients. Okay? It doesn't always have to be x for both of the products. It just was in this case because those are both single coefficients. Okay? So, here, let's do green. That's the only reason we do that. Okay. So if that's x, then HI was minus 2x. Okay. So that's all we can get from the ice table right now, right? Because last time you were given an equilibrium concentration, which we could use for x, and we could solve all those. Okay? But if you're not given any equilibrium concentrations, you can use the given equilibrium constant. Okay? Let's write what fractions would make it up. What concentrations would make it up in its fraction. Okay? So what concentrations would we need up on top of this fraction? Concentration of what? H2
times I2, right? Over what? HI, but squared. Okay. And are those concentrations at any time or initial or at equilibrium? Okay. That's very important.
Okay. So what do you suppose we could substitute in for those, for the H2 and the I2? Yeah.
X. X times X is X squared. Okay. Then what? Over close. Oh. Squared like that?
No.
Okay.
You'll be tempted a lot of the time to skip this step and just go straight to writing these things. I encourage you, as you're still getting used to doing this, to start by writing it in terms of the concentrations, because you're more likely to remember to include the coefficient as the exponent there. Okay? That's the number one mistake at this point, okay, in the problem, to forget about the coefficients. A general rule of thumb here is that the coefficient actually gets used twice. What do I mean by that?
It's used once to figure out the what the equilibrium concentration is.
We used it for the stoichiometry of 2 moles of this for every 1 mole of that. And then the other place we used it was as the exponent in the equilibrium constant expression. Okay? So that's a quick check to do to make sure that you don't make that number one mistake. Okay? And then let's just rewrite this equation that we've made. 1.26 times 10 to the minus 3 equals x squared over 0.22 over 225 minus 2x squared. Okay. And then we got a little bit of algebra to do. Any suggestions for solving for x here? What? Somebody said. No? Multiply both sides by the denominator. Oh, what would be better about taking the square root of both sides? We can get rid of the exponent immediately by taking the square root of both sides, because that's the same as x over okay. So if we did the square root of both sides, 1.26, 10 to the minus 3, that gets rid of those exponents. To x. Okay. And then we can do what Katrina wanted me to do, right? We can multiply the denominator, right? So okay. Then what? You can evaluate that square root at any point too, but how do you deal with those parentheses? Yep, you have to distribute. Okay. Okay. So why don't you evaluate the square root and distribute, and we'll compare our numbers. Always be careful of your signs when you're multiplying a constant through especially subtracted terms like that. So after you distributed, you should have two terms on the left and equaling x on the right. This first one is going to be just a number, right? Because 1 by 2, 6, 10 to the minus 3 is a number. We multiply that by this number. Did somebody get that first number over here on the left? 0 point something. Let me get that. Yeah, that's what I got. 0.08599. If I were you, I would evaluate that square root first before you multiply it, just so you're not having to deal with parentheses and order of operations and stuff in your calculator. That's where mistakes can happen. No? You don't. The other one should be minus, right? Minus 0 point what?
0.0709.
Yep, that's what I got. 0.7099.
And those are multiplied together. No, they're not.
Nope.
No, they're not. Okay.
Nope, this is minus 0.07099, but I need something else. X equals x. Okay. And that's just number crunching. Then what? Add the 0.07099 to what? How do you add? Yeah, how do you add 0.7099? How do you add that to x?
Just to add 1 to
Yes,
it,
you add it to 1, because that's the coefficient of a lone variable, right? So you don't need a calculator for that. 0.008599 equals 1 point. X equals so 8029 originally came from 3 sig figs, I think so. All right. So just a little bit of super fun algebra to solve for x in an equation that involves exponent. this was actually, we were actually a little bit lucky in this one because we could get rid of that exponent all at once right at the beginning. Okay? You can imagine what's going to happen on the next page. But now that we have x, what does that mean? X is the concentration of what? Products at equilibrium. Okay, so X equal, or here, let's just write it right here. H2 at equilibrium, which is the same as I2 equilibrium, is X 803. I'm going to round that now that that's an actual answer. Okay. What will I do for HI?
And subtract that number times 2.
I got 0.226. Sound like right? Okay. Now, that's what we were asked for. It said, what are the equilibrium concentrations? So we've given concentrations for the reactants and products at equilibrium. It is very important, however, that we go back to the equilibrium and make sure that these numbers make sense. Okay? Because there is a ton of algebra that happened in there, and you can very easily get completely ridiculous nonsense numbers that you would think nothing of unless you went back to check to make sure it made sense. So 0.24225 is what we started with. That concentration obviously should be going down as we reach equilibrium. Okay? We started with 0.242. We ended up with 0.226, so the concentration went down, just like we expected. Okay? We have a positive concentration of product. That's good. Okay. Now, look at the size of these numbers. At equilibrium, we have obviously much more reactant or product. We have much more reactant at equilibrium. Does that make sense with the size of our equilibrium constant? Yeah, that's a fairly small equilibrium constant, quite a bit less than 1. Okay? If it was equal concentrations on the top and the bottom, K would be 1, pretty much. Okay? So a small equilibrium constant means that our equilibrium will be heavily reactant favored, okay? Which means that the concentration should not be changing very much from initial. Okay? We'll be reducing the initial concentration by a little bit, and we'll be producing a little bit of product, but it'll still be mostly reactant. Okay? So again, that makes sense. These are consistent with a small okay, make sense? So in general, what we did is we set up our ice table using our x's in the change row and just modified our equilibrium based on the amount that it should be changing. Okay? We plugged those into the equilibrium constant expression and solved for x. Okay? You can do that if you're given an equilibrium constant, if you're given a k value. Okay? Questions about that one? That look good? Okay. Now, I mentioned that we were actually kind of lucky on this one because we had a quantity squared on top and a quantity squared on the bottom, which meant we could take the entire square root of the whole thing. Okay? That's a direct consequence of having two products and coefficient 2 of a single reactant. Okay? And there are a lot of reactions that do that, but definitely not all of them. Okay? So, try this one. One reactant and two products. Given equilibrium constant, I would like you to try to do what we just did. Okay? Fill out the ICE table, have your equilibrium row in terms of x, substitute those values into the fraction for the equilibrium constant, and we'll compare when we get to that point. Okay? And then we'll work together at solving for x. Did you get an equation here involving your x's? What's on top? X squared over. Okay. Great. So let's rewrite that. Okay. So no quantity squared at the bottom, so now we have to start by multiplying by the denominator. So, everybody get this far, by the way? Everybody good with that? Okay, should have been able to do that. Okay, so 8.3, 10 to the minus 4, quantity 0.50 minus x equals x squared. Okay. What is 8.3 10 to the minus 4 times 0.50? You can almost do that in your head. 4.15, yep. Minus, and since that's just an x, it has the same value, 8.3 10 to the minus 4 x squared. That's a strange looking 4. Okay. So, how do we have to arrange this now? Everything has to go on the same side and be set equal to 0. And we have to use the quadratic equation. Okay? So, it ends up being easiest if we keep this coefficient of positive 1. So what I would recommend is doing x squared and then changing the signs of the other ones. Plus 8.3 10 to the minus 4x minus 4.15 10 to the minus 4 equals 0. This is a quadratic equation. Dun dun dun. Does anybody know how to solve a quadratic equation? Well, the solution of the quadratic equation, x equals what? That's right. Absolutely. By the way, a lot of people call this the quadratic equation, but that's the solution to a quadratic equation. This is the quadratic equation.